So we were discussing about rate proportional servers, and we saw that in the rate proportional servers, session can be in any one of these four states. That is, it could be either in the idle states, or it could be in the active state, or it could be in the backlogged or non-backlogged states. Okay, so we were discussing in the previous lecture about the state transitions of the sessions various states. So let me just revise that. So what we are saying is that session could be in the inactive state, that is the idle state, and when a packet arrives, the session becomes active and backlogged. Okay, so we say that a session is in active state if the session's potential is greater than or equal to the system potentials. Okay, so when the session is inactive and when a packet arrives, the session's potential is updated and may be kept equal to the system potential. So in that case, it's active and also the backlogged. Now as the session starts receiving service, then the session's potential increases, and when all the traffic has been served, okay, the session remains active because its potential will be more than the system potentials, but since all the traffic has been served, it will be now not backlogged. Now if the session continues to be in this state, that is the active but not backlogged state, then what will happen is that the session's potential, the session's potentials will remain constant now because the session is not receiving any service. But on the other hand, the system potential will keep on increasing. So as a result, a time may come when the session's potential may become lower than the system potentials. Now when that happens, as we had seen, that the state moves from the active but non-backlogged state to inactive state. The state moves here. But on the other hand, if the session potential was greater than the system potential and the session was not receiving any service, that is, it was not having any traffic also, that means it was not in backlog state, and then suddenly if the some traffic arrives and the queue becomes non-empty, then the session can even move to the active and the backlogged state. So you can see, in the various cycles that the active period starts here at tau for the first time. Here the state was inactive here. So when you become from inactive to active, and the active period starts here at tau, your backlogged period also starts because the traffic has arrived, and at this point all the traffic which was there, which was there here or which arrived during this period has been served, and the session therefore enters a non-backlogged period. Now during this period, the session's potential is still higher than the system potential, and at this point some traffic might arrive, and therefore the session moves into the backlogged period. Again, session's potential keeps on increasing. At this point, all the traffic that arrived during this period has been served, and therefore the session moves into a non-backlog period. Now in this non-backlog period, the session's potential is not increasing, but the system potential keeps on increasing, so that at point, at time t, the session potential will become lower than the system potentials, and the session then moves into here and inactive states. Right now, this is what we have seen. The state transitions in the rate proportional servers. Now as we had asked this question, that what about in the fluid flow of air queuing algorithm or in the GPS server? So we see that in the GPS server, the session will either be in the backlogged period or it will be in the non-backlogged period. Okay. So when the session is in the backlog period, okay, at time tau, the session becomes backlogged and the session starts receiving service, and during this period the session's potential is also equal to the system potentials, okay, because the system potential in the case of a fluid flow server is always equal to the session's potentials in the fluid flow GPS servers. At this point, all the traffic that arrived during this period has been served, and therefore the session enters the non-backlog period. Now during this point, the system potential will keep on increasing, and it will be again equal to the potentials of those sessions, you know, which are backlogged during this interval. But since this session is idle, its potential is not increasing. Okay, so now the question is that let us say that t is in any time period during this backlog period in the GPS server, then it is clear that the service received by the session I during the period tau to t is always greater than or equal to rho I, where rho I is the rate allocated to the session I into t minus tau. Okay, now this is always satisfied. Okay, this condition is always satisfied during the backlog period. So I should say that this condition is always satisfied for GPS server during backlog period. For GPS during backlog period, that is what we are saying, that the service received by any session during a subinterval, and this during a subinterval of the backlog period is always greater than or equal to rho I into t minus tau. Whether this is true for rate proportional servers, you know, whether this is true for rate proportional servers, no. Okay, this will not be true always for rate proportional servers. That is, for rate proportional servers, you know, if we say that tau tau to t is any subinterval of a backlog period, then for rate proportional servers, you know, the amount of traffic, that is wi tau t, will not be greater than or equal to rho I into t minus tau. Okay, so why it is so? Because it may be just possible that a session can be backlogged. Okay, the session can be backlogged in a rate proportional server, but still it may not be receiving any service in the rate proportional servers. So that is possible, because it is possible that the service of a particular session may get temporarily suspended in the rate proportional server, and this will happen if the total service received by this particular session has become greater than the minimum service. Okay, and its potential is not minimum, so that the other sessions who have minimum potentials, you know, they will be served. Okay, so it might be quite possible that a particular session, even though it is backlogged, its service may be temporarily suspended in the rate proportional servers. So as a result, you know, this particular relationships will not hold good. Then what kind of relationships hold good in the RPS? So what happens in the RPS? So let's see. If this relationship does not hold, then, you know, what happens in the RPS? So in RPS, if we see that if tau is the beginning of an active period, if tau is the beginning of an active period, okay, then this result will be guaranteed. Okay, so if tau is the beginning of an active period, and then for this is for any t during this active period, right. So this result, you know, needs to be proved. So on the other hand, as we had seen that in the case of a GPS server, this result will hold true for any tau to t, any interval tau to t, which is a sub-interval of the backlog period. But this result does not hold good for the rate proportional servers. However, for the rate proportional servers, if tau is the beginning of an active period, then this result will hold good. So if you can see here that this is the rate proportional server state transition diagram. So if tau happens to be the beginning of a active period, and if t is any time here, okay, and let's say the time at which this ends is tau prime, if t is any time here, then the amount of service received by a particular session I during this period of tau to t, okay, will be greater than or equal to rho I into t minus tau. Let us prove this result, okay. So I'll try to give a sketch of this proof, okay. So we know by definition, okay, the potential, the session's potential, the potential of the session I will be always greater than or equal to the system potential at time t, okay, where t is any time during the active period. So during the active period, by definition, the session's potential is always greater than or equal to the system potential, right? That is by the definition of the active period. Now tau is the beginning of the active period, okay, that is when the session has just changed its state from an inactive period to the active period. So tau is the beginning of that active period, okay. So therefore at that point, the tau, okay, the session's potential will be updated and it will be made equal to the system potential. So therefore p I tau is actually equal to p tau, okay. Now you know, by definition of rate proportional server, by definition of rate proportional server, okay, the difference in the system potential, that is pt minus p tau, will be greater than or equal to t minus tau, okay. But you know, pt is actually, pit is actually greater than or equal to pt, and pi tau is actually equal to p tau. So therefore this implies that pit minus pi tau, they are greater than or equal to t minus tau. But during the active period, okay, the session potential, the increase in the session's potential, that will be equal to the normalized service the session has received, okay. So pi tau minus pi tau, okay, that is the increase in the session's potential, is always equal to wi t tau upon rho I. Now this is the normalized service received by the session I during this active period, okay. So therefore, okay, this should be wi tau t, okay, will be then greater than or equal to rho I into t minus tau, and hence you know we have proved the result, okay. So what does it say is the service received by a particular session I during a subinterval of the active period, starting from the active period, you know, and during any interval of the active period, the service received by a particular session I will be greater than or equal to its allocated rate into the durations, okay. So this is the result we have proved. Note that this result holds true for any subinterval of the backlogged period in case of a GPS server, generalized processor sharing, or fluid flow fair queuing server that we have been discussing. However, this result does not hold true in the case of a rate proportional servers, that the service received by a particular session I will be greater than or equal to its allocated rate times the time durations, okay. Because in the rate proportional server, a particular session, even though it is backlogged, may not be receiving any service. Its service might have been temporarily suspended because its system potential may not be the minimum, and other backlogged sessions, you know, which are having minimum system potentials, they are being served, okay. So therefore the service of a particular session may be temporarily suspended also, okay, and therefore it is possible that a particular session is not receiving service, and that will happen only if a particular session has received more service than its minimum guaranteed service rate. Now another thing is we also see that the backlog periods of two servers need not coincide. So this also shows that the backlog periods of two servers may not coincide. Why? Because in the GPS server, that is in the fluid flow fair queuing server, if a session is backlogged, then it will always receive its service, and the system potential, or as it is called system virtual time in the GPS servers, that will increase in proportion to the normalized service received by the backlogged sessions. And the normalized service received by two sessions that are backlogged in the GPS is always equal, okay, during any sub-interval of the backlog period. So the service received by the backlogged sessions is always equal during the backlog period for the sessions in the GPS servers, but this may not be true in the case of a rate proportional servers, and therefore as we have seen that the backlog periods of the rate proportional server may not be the same as the backlog period in the case of a GPS servers. Okay. So now if this is so, then now we suppose we want to compare the two scheduling algorithms in terms of fairness or the delay properties, then this question obviously arises that if the backlog periods of two servers are not coinciding, then how do we compare the two servers? Now towards this purposes, to compare the properties of two scheduling algorithms, we define some notion of a session busy period. We have already seen the notion of a system busy period. What is the notion of a system busy period? The system busy period is any interval of time during which the server is always busy. Okay, the server is always busy. It is servicing some packets or some traffic. This is what is called as a system busy period. We now introduce the notion of a session busy period. Okay, so let us see what is the notion of a session busy period. Session busy period. Okay. So the session busy period is a maximal interval t1 t2 such that for any t during this interval of t1 t2 we have the arrivals, that is ai t1 into t is greater than or equal to rho I t minus t1. Okay, what does it mean by these relationships? It means that the arrivals which have occurred during the interval t1 to t2, that is the number of arrivals. Okay, so session busy period actually starts here at t1 and it ends, we are saying that it ends at t2. Now this t is a time interval here. What does it see? It says the number of arrivals that will occur during this interval, that is t1 to t2, is always greater than or equal to rho I into t minus t1. It means that if the session was served with exactly the rate as rho I, okay, not more, not less. If the session was served with exactly the rate rho I, then this session will remain continuously backlogged, okay, during the interval t1 to t. Now during this interval, it shows that if this relationship is true, then this session is backlogged. And obviously, if this relationship is true for over this interval t1 to t2, okay, then we say that the session is in busy period. This is called a sessions busy period. Now note that in the actual server, the session may actually be receiving more service than its minimum guaranteed or allocated rate of rho I. It may be quite possible, because if other sessions are empty or non-backlogged, if they do not have any packets, then this ith particular session may be receiving more service than its guaranteed allocated minimum rate also. That may be possible in a particular scheduling algorithms. But we are now defining a hypothetical server. We are saying that there is an hypothetical server, and in this hypothetical server, suppose if you serve the sessions with the rate rho I, then if we can say that the number of arrivals, okay, during any sub interval of a particular period is always greater than or equal to, okay, rho I times, you know, that interval, that is the service received by this particular sessions. If the number of arrivals is greater than or equal to the service received, or the number of you know, traffic, or the traffic, the amount of traffic that has been served, then this particular session will remain backlogged. So this is, you know, session busy period is therefore defined with respect to a hypothetical server, and therefore the busy periods of all the sessions will be equal irrespective of the fact that we have used different scheduling algorithms in different cases. Okay, so the sessions busy period, you know, sessions busy period will be same for all scheduling algorithms. Now this is an important notion, and therefore what we would like to see is that we would like to understand the behavior of a particular scheduling algorithms during a sessions busy period. That is what we would like to do. Okay. Now sessions busy period, let me just draw it, you know, graphically. It looks something like this, that here are the arrivals. Arrivals are the staircase, because the arrival increases whenever the last bit of a particular packet has arrived. Okay, so here is a sessions busy period. This curve has a slope rho I. So you can see that during this interval the arrivals is always greater than or equal to rho I into T. After this, you know, the arrivals are going to become greater, sorry, the service is going to become greater, and therefore this will not be the sessions busy period. So this is the sessions busy period. Okay. Now we would like to study, you know, we would like to ask these questions, that how the busy period is related. Okay, so how busy period is related to active period, how busy period is related to active period in rate proportional servers. This is the questions that we would like to ask, and the answer of this question is that basically we would like to ask that in what way we can relate the sessions busy period to an active period in rate proportional servers. Now again I want to emphasize here that the sessions busy period is defined with respect to a hypothetical server in which the server is serving with a rate rho I, and what we are saying that if the server serves with a rate rho I, then the sessions busy period is that maximal interval of time during which the number of traffic arrivals exceeds the amount of service received by the session I. Okay, so that is how we define the sessions busy period. Okay. The systems busy period is any interval of time during which the system remains busy. So note that systems busy period, the systems busy period for all scheduling algorithms will coincide. Okay, we have seen that a backlog periods for different scheduling algorithms may not coincide. However, the sessions busy period will also coincide. The question now that we are asking is that in what manner the sessions busy period is related to the sessions active period in a rate proportional server. So the answer is that if tau is the beginning of a session I busy period, tau is the beginning of a session I busy period in rate proportional servers, then tau is also the beginning of an so we say that if tau is the beginning of a session I busy period in rate proportional servers, then tau is also the beginning of an active period. So we will try to prove this by contradictions. So we have a proof by contradictions. So we take a case. So case 1 is if tau is in inactive period. So the tau, what we are saying is that tau is the beginning of a busy period, but tau lies in the inactive period, assume. So something like this. If tau is the beginning of a session I busy period in a rate proportional server, so by contradiction, so what we are saying is that tau lies in an inactive period. So this period is active and this period is inactive. Let us say that tau is here. Now since session I was not busy before tau, and the session becomes busy at t, then and the session becomes busy at tau, then a packet must have arrived. So therefore pi tau should be equal to p tau, and then but that means that tau is the beginning of an active period also. So which is a contradiction? And therefore this is not possible, that tau cannot be in the active period. So this is the first case. So therefore tau becomes the beginning of an active period if you try to prove that tau is in the active period. So since what we are saying is that since session I was not busy before tau, it became busy before at t only, and here it was in inactive period, then here the packet must have arrived. So that means tau must be here, their inactive period must end here actually. So since I was not busy before tau, and the session became busy at tau, then since session becomes busy at so a packet must have arrived. And therefore pi tau should be equal to p tau. So this is first case where tau is in the inactive period. So we will now try to prove the second case when tau, case 2 when the tau is in the somewhere in the active period, something like this. Okay. So case 2 is when tau is in active period. So this is something like this, that here is an active period, again inactive, active, inactive, so on. So let us say that this is the tau. Okay. And let us say that tau naught, let tau naught denote the beginning of active period, right. Now let us say any t belonging to tau naught to t. Now since t is in active period, okay, PIT, that is the sessions I potential at time t, should be greater than or equal to the system potentials. Now since tau naught is the beginning of the active period, we should also have that PIT minus PI tau naught, okay, during this interval, it should always be equal to Wi tau naught t upon rho I. This is by definition of the active period. Okay. Now since tau naught is the beginning of an active period, okay, so since tau naught is the beginning of active period, it also means that Wi tau naught t should be greater than or equal to rho I into t minus tau naught. Now since before tau naught the system was not backlogged, okay, before tau naught the system was active, therefore we also have this relationship before tau naught, okay, system was not backlogged, AI tau naught t should be greater than or equal to Wi tau naught t. Now which also means that this should be greater than or equal to rho I t minus tau, which also means that t belongs to the same busy period that covers the interval tau naught to tau, and therefore which means tau cannot be the beginning of the busy period. It cannot be, or the tau naught cannot be the beginning of the active period. Then the tau naught has to be equal to tau. So therefore, sessions, what we have really tried to prove here is that if tau is the beginning of a busy period, then it is also the beginning of an active period in a rate proportional servers. Okay, so in a rate proportional servers, what we have tried to prove is that if tau is the beginning of a sessions I busy period, then it is also the beginning of an active period in a rate proportional servers. Okay. So we have proved this result by contradictions. Okay. So two cases we had considered, whether the tau is in the inactive period or tau is in the active period. So by considering these two cases, we have tried to prove this result, that if tau is the beginning of a session I busy period in rate proportional servers, then it is also the beginning of an active period. So we now introduce the notion of a latency rate servers. So I just define the notion of a latency rate servers. Now the definition of the latency rate servers is that so let tau be the starting time or the beginning of jth busy period of ith session, jth busy period of ith session, and let tau star be the time at which the last bit arrived during this jth busy period has been served, during jth busy period has been served. Then we define a latency rate server is the definition. By definition, we define a latency rate server, okay, is a server for which a non-negative constant can be found non-negative constant C can be found such that for any t which lies between tau to tau star, okay, we have this relationships, okay, for any t between these two things, W ij tau t, that is the amount of service received by ith session in the jth busy period during the interval of tau to t, this interval of tau to t of the jth busy period, that is greater than or equal to max of 0 or rho I times t minus tau minus the constant c. Now this includes, this gives you total service provided by the server to the traffic of the session arrived during jth busy period. Now the minimum value of C that satisfies this is called the latency of the server, okay. So the minimum value of C satisfying this is called latency of the server, okay, which we call it to be latency theta r. So just to show you how the latency concept looks like, it will be something like this, that this is let us say the service wij tau so here is what we are saying is the minimum okay the duration minimum theta I, and this has a rate of rho I, and this denotes wi tau t. Okay. So this is what is called as the latency of the server. Now this latency also has a significance that the minimum time that a particular session has to wait before it actually starts getting its service. Okay. So the importance of the latency is that the minimum amount of time a particular traffic session may have to wait before it starts getting service by the server. Now we will actually prove that an RPS, a fluid RPS server, a rate proportional server, is a zero latency server. We will also prove that a fluid GPS server, a generalized processor sharing server, is also a zero latency server. Okay. We will then prove the latencies of, then we will try to determine the latencies of various servers, and from the latencies of the various servers we will try to prove the delay bounds of a packet scheduling algorithms. Okay. So now let us prove first an important result with respect to the latency rate servers. Now this result states that let T1 to T2 be a busy period of session I, then all packets that arrived from session I during this period during this busy period will be serviced by the time T2 plus theta I, where theta I is the latency of the server. Okay. So T1 to T2 is the busy period of the session I, and all packets which have arrived from session I during this busy period, they will be serviced by T2 plus theta I at most, where theta I is the latency of the servers. So the proof is, let us say that the last packet, of the busy period of this session it completes service at time t. Then it is clear that the amount of traffic which came during T1 to T2, that is equal to Wij, and let us say that this is the jth busy period. Wij T1 to T, right? Because by definition Wij denotes the amount of service received by session I during the jth busy period for all that traffic which arrived during this jth busy period. Okay. So from the definition of the busy period, you know that AI T1 to T2 is actually equal to rho I T2 to T1, which therefore is equal to Wij T1 to T. but from the definition of the latency rate server, Wij T1 to T is greater than or equal to rho I T minus T1 minus theta I. This is by the definition, which if you substitute here, then which also means that rho I T2 minus T1, rho I into T2 minus T1 is greater than or equal to rho I into T minus T1 minus theta I, which also implies that T is less than or equal to T2 plus theta I. What is a T? T is the time at which the last packet completes its service. So what we are saying is that the time at which the last packet completes its service is less than or equal to T2 plus theta I. T2 is the time at which this particular busy period ends, and theta I is the latency of the server. Okay. So this is an important concept from which we would try to derive the delay bounds of a particular packet scheduling algorithms. Okay. Now what we are trying to derive now is that if the input traffic to these rate proportional servers, okay, which are also latency rate servers, by the way, the rate proportional servers are also latency rate servers, and we will shortly prove that the latency of a fluid rate proportional server is 0. So these rate proportional servers, which are latency rate servers, if the input traffic to these latency rate servers is rho sigma regulated, where the allocated rate to the server rho I is now equal to or proportional to the average rate rho of that rho sigma traffic. If the two are equal, then we will try to derive the delay bounds for the particular packet scheduling algorithms. Okay. So now we prove a very important result, okay, for the delay bounds of a packet scheduling algorithms which are latency rate servers. Now since most packet scheduling algorithms that we have studied, like WFQ, weighted fair queuing algorithms, or generalized processor sharing algorithms, or rate proportional servers that we have all studied, they are actually latency rate servers. All these scheduling algorithms are latency rate servers. So therefore this delay bound that we are deriving will be general enough, and its result will be applicable to all the packet scheduling algorithms. Okay. So we will now state the result for the delay bound of a packet scheduling algorithm. So that result we now state, and that result is now if S is a latency rate servers, okay, so this is a delay bound of a latency rate server. Okay. So we will try to prove is that if the traffic in a latency rate server for session I, okay, is rho sigma regulated, is sigma I rho I, then the maximum delay, the di of any packet of session I is given by di is less than or equal to sigma I upon rho I plus the latency. Now this is an important result which is trying to say that if we know the latency of a particular packet scheduling algorithms, then we can determine what is the maximum delay that the packet of a particular session will suffer if being served by the particular packet scheduling algorithms. Okay. All we need to know is the latency of that packet scheduling algorithms. Okay. So what we will do is that we will first try to prove this result, and then we will try to derive the latencies of the standard scheduling algorithms like rate proportional servers that we have derived and the weighted fair queuing scheduling algorithms. So we will try to do this in our next lecture.